Hi folks, well welcome to the third of the circuit rules lessons, and we're now moving on a wee bit to looking at combination circuits of series and parallel. So for today's lessons you're going to look at solving circuits for currents in combination circuits of series and parallel, and solving circuits for voltage in combination circuits of series and parallel. So what we're going to focus on first of all is looking at current in combination circuits, and you might ask, well, what is a combination circuit? Well, for me, a combination circuit is one which contains both series and parallel circuits joined together. So how do we deal with these circuits where they're not series, they're not parallel, they're a bit of both? Okay, so let's start with a wee bit of revision first of all, which is this one here. What is the current? So I'm going to give you, say, sort of 15 seconds starting from now to think about what the answers for I2 and I3 are. Okay, so hopefully you didn't find that too difficult, because this is actually a revision question. We did this in the previous lesson, which if you're following straight on, you'll probably recognize it. If you're not, then it's a good way just to test your understanding basically. So remember, this is a parallel circuit because there's two or more ways for the current to flow through. Notice how I'm using my series circuit rules. And then if we think about it, there's 5 amps going down here, and then 2 of the amps goes along the way to the bulb. So that means there must be 3 amps left to go around the rest of the circuit. And then that means the current flowing around here is 3 amps, and it's still 3 amps going along this branch because technically this bit is in series. So in a way, we're already looking at combinations of series and parallel circuits. Okay, and then obviously the 3 amps keep going along the bulb here, and then it joins up with the 2 amps here to make up a total of 5 amps going back along to the supply, the cell, which is exactly what we'd expect it to do, because remember, we can't have more amps than we started off with. Okay, so this is the type of circuit we want to kind of focus on. You can see that there is a wee parallel bit down at the bottom here, and then there's a wee series bit here, and the cell is a wee bit right opposite way around. It's a negative on this side and the positive terminal on this side. And the idea is that the current will go round this way. Okay, and although this looks like something you've never seen before, and it looks quite difficult because it's complicated, the nice thing about physics is it's about learning rules and applying those rules in different contexts. But once you get the hang of applying the rules in one situation, as long as you are able to follow that procedure, it's the same thing. And this is where physics can become easy if you know how to do that. And if you don't know how to do it, you practice it, because the more you practice, the better you'll get at it. So first of all, let's look at the series part. Now, the series part is just this bulb. How do I know it's series? Well, how do you know something's always in series? Because there's only one way for the current to flow. So here you can see there's only one way for the current to flow. So that means it must be in series. Can you tell me what other parts are in series? Going to give you 5 seconds to tell me which other part in series starting from now. So did you get that? This part here is the bit that's in series. Why? Because again, there's only one way for the current to flow. So what is the current at I1 and I4? Well, the series circuit rules are that current stays constant. So we know that I1 must be 5 amps and I4 must therefore also be 5 amps as well. Now, having seen how those series circuit rules are applied, I'm going to let you try to find out I2 and I3. You've got 15 seconds starting from now. Okay, so how do we know, first of all, whether it's in series or parallel? Well, again, think about the current. It's coming along here. It then splits in two, so that means it must be parallel. Now, the rules for current and parallel is that current splits up. What we're assuming here now is that these two bulbs are identical. We're not told otherwise, so we have to assume that. So that means 5 amps will split into 2.5 and 2.5 for both branches of that circuit there. Okay, not going to draw the other one because you can see it. And then obviously what happens is when the current comes along back here, they join up together and that gives you the 5 amps there. Okay, now if you found any of that difficult, I would recommend you to replay this slide again. Really make sure you understand this because the next couple of examples will all be using the same process. Okay, so to summarize that process, identify the series and the parallel parts of the circuits, apply the series circuit rules to the series parts, apply the parallel circuit rules to the parallel parts, and that's it. So let's look at another example here, folks. So notice we've got a fairly similar circuit here, but we've got a motor instead of a bulb. So going to give you 15, well, let's call it 10 seconds to get the answer starting from now. Okay, so hopefully fairly straightforward here. You've got series, so that's 2.5 for I1 and 2.5 for I4, just for the same reason as before. Now the interesting bit here is the parallel circuit, because notice you've got 1 amp here and you don't know what the current through the bulb is. So obviously current splits up in parallel circuits, so 2.5 minus 1 means this is 1.5 amps. Now, the question that I'm hoping you're going to ask yourself, or me, if I was in class, is why is it that these two currents are different, right? Can you think of a reason why these two currents are not the same compared to the previous example? Give you sort of 5 seconds to think about that starting from now. Did you get the answer that the reason why is because they are not identical? Right? The motor and bulbs are two different components, so therefore we can't say the current will split evenly through the two of them. Even if it was another bulb, unless the bulb is identical, you can't say the current's going to split evenly. We have to assume that if they don't tell us, which is what we did in the last example there. Okay. Now, another example, this is a bit of a trick one. I don't usually like doing this because I always think, you shouldn't be given trick questions unless you really, really know your stuff. So have a wee think about this. You might recognize this circuit from National 5, okay? So number one, what's the current at I1 and I2? And what do we call this type of circuits? You've got 15 seconds starting from now. Okay, so hopefully you got the answers was, first of all, it's a series of parallel circuit. Well, if we look at it, we can see there's only one path for the current to flow at I1 and at I2. So that means the answer is 5 amps. And notice how I'm using the exact same method as before. I'm asking, how do I know it's series or parallel? And then using my series or parallel circuit rules to solve it. Now, the reason why this is a trick question is when you get to here, some of you might think, well, it's got two paths, so the current must split up, so therefore it must be a parallel circuit, which you are kind of right. Then you might say, well, okay, it's a bulb and a wire, so how does the current split up? And this is where you might have a wee problem. Okay, and we call this a cognitive conflict if you want to be fancy. Because how do we know how the current will split up between the bulb and the wire, right? And it's a trick question because if you remember from the previous lesson, current will always take the path of least resistance. So in this case here, the bulb will have a higher resistance than the lead, so therefore the current will actually go through the lead and the bulb will have no current. So that means the bulb here will not be on, all the current will flow through here. Okay, and that's actually quite a dangerous thing, and we call that a short circuit. So this wee sort of line here, this lead here, is called a short circuit. Okay, so just be aware of that because we will come back to this idea of short circuiting things later on when we do capacitors. So just be aware of that one there. It's a wee bit of a trick question. Now, this is going to be your final example for current in combination circuits. So have a go at this one. Again, I'll give you maybe about 10 seconds because by now I think you're pretty good at this. So 10 seconds starting from now. Okay, and hopefully you got fairly straightforwardly. Remember, it's a series of parallel, it's series, so this is also series as well, and this must be parallel. So here you should have got 5 amps for I1 and I4 because they're in series. I2 and I3, did you remember that you can't tell how the current splits up if they're not identical? So the answer for this one is we can't tell what I2 and I3 is. Unless we know one of these, we won't know how the current will split up because they're not identical components. So a wee bit of a trick question there. It's about being observant and remembering all these wee extra bits to the rules. Okay, so hopefully you're confident with that. We're now going to move on to look at voltages. So voltages in combination circuits now. The nice thing about physics, as I keep saying, is once you kind of learn one set of rules, the other bits of physics is usually using the same kind of set of rules or the same process, but just in a slightly different context. So with voltages in combination circuits, we're going to do the same as current, work out if a circuit is in series or parallel, and then apply the rules for voltages accordingly. Okay, and if you recognize that process, it's going to save you a lot of work in the long term because there's going to be a lot of other stuff you need to remember how to do. So this helps you a wee bit, folks. Okay, so nice straightforward example. Going to give you, say, about 6 seconds to do this one starting from now. Okay, hopefully you all recognize this one's dead easy. First of all, it's parallel because there are two paths for the current, the voltage to go, the current, sorry, to pass through. And remember, voltages is constant in parallel, so the answer there is 6 volts for both of these. Okay. Now, you've seen this circuit before because we did this for current previously, so I'm going to let you try and figure out how to do this one yourself. So I'm going to give you 15 seconds starting from now. Okay, so first of all, although we're talking about voltages, it's still useful to think about current because that lets us work out if it's series or parallel. So just like before, there's only one path to go through. So V1 is in series and V4 is in series as well. And we know that voltages split up in series. Okay, voltages split up in series. Now the problem here is obviously we've got a parallel bit because we know that the current will split up here. Okay, so instead of looking at the series, first of all, we need to look at the parallel bit. So the parallel bit, remember, voltages in parallel is constant, so V2 is 2 volts, then this must also be V3 must be 2 volts as well. Okay, so just to recap that, voltages in parallel are constant, so if one voltage is 2 volts, the other one must be 2 volts as well. Going back to the series circuits, we now have V1 is in series to this parallel bit. So if there's 2 volts going across all of this, that means there must be 4 volts going across the bulb here because voltage is split up, right? V4 is technically a wee bit of a mistake by me. You wouldn't really have V4 there because V4 you really need to have a component in there for there to be a voltage there. So I'm going to scrub out V4, ignore that one just now, folks. Okay, so hopefully that made sense. If it didn't, please go back and review it again. And just like before, I've given you a spare slide there, just there for you to kind of work through again. So pause the video if you want to try that one yourselves again. And remember, ignore V4. Okay, so example number 3 now. Let's try and see if we can solve this. So again, I'm going to let you try this first because I think by now you should be getting an idea of the process. So I'm going to give you 15 seconds starting from now. Okay, as before we start, let's miss out V4 because that's not important. So V1, we know it's in series. Because there's only one way for the current to flow. V2 and V3 are in parallel because there's 2 ways for the current to flow. Notice how I'm using the same process as before. I'm always doing the same thing. I'm just trying to fit it to the context of the question. Okay? So here we know that V3 is 1.5 volts. Voltages in parallel are always the same or constant. So V2 must be 1.5 volts as well. Okay. Now notice the difference from current, right? Before in current, we couldn't really say what M and the voltage across M and the bulb were unless we knew one of them. But here we don't really need to bother because current is the same everywhere in a parallel circuit. So that's the nice thing about voltages. Now, if we know there are 1.5 volts across the parallel circuits, that must mean there is 2 volts across the bulb because the bulb is in series to the motor and the second bulb. Okay, so don't get confused. Whatever the voltage is here, it's constant for both of them, and then you work it out for the remaining one by subtracting this value from the supply voltage. Okay, hope that was clear. If it's not, try and play the slide again. Now, can you remember the name of the circuit? It's called a short circuit, isn't it? Okay, so what's the voltage going to be across that bulb? I'm going to give you 10 seconds to think of an answer and a reason why, starting from now. And the answer I hope you put down was actually 0 volts. Okay, now why 0 volts and not 9 volts? Because you might say, well, Mr. Lamb, isn't that a series circuit? And there's only a bulb there, so surely it should all be 9 volts. It should all go across this bulb. Well, the question I want to ask you then is there any current flowing through the bulb? And the answer should be no, because remember, if it's a short circuit, the current will take the path of least resistance. So therefore, it means there's no current going through the bulb. If there's no current, there cannot be any voltage either. So it's a bit of a trick question, but it's a very nice question to see if you really understand the physics by being able to put together different bits of physics. And that's the type of thing you want to be able to do if you want to aim for a really, really good grade. Okay, folks? Okay, folks, we now come to our final example of voltages, and I'm going to give you 15 seconds to come up with the answer starting from now. Okay, going to cut it a wee bit short there because I think you might have got the answer already. So first of all, this is in series, so that's 3 volts across the bulb, that's in series. So how much is left to go for the parallel bit? Well, it would be 10 minus 3, which is 7 volts. So what's V2 and V3? It will be 7 volts. Notice the difference from the current situation, because in the previous example with current, we couldn't work out what the current was because they weren't identical. With voltages, it doesn't matter because voltages is the same everywhere in a parallel circuit. So notice that wee variation from current and voltages. And you'll develop that kind of problem solving skill the more of these you do. So don't worry if you didn't get this wee trick question here. If you see more of these, if you practice this, you will get good at it and this will not be a problem. Okay, so the final slide is putting it all together. Can you work out all the missing currents and voltages? I'm going to give you 15 seconds starting from now. Okay, now this is a classic type of problem in physics where it's very complicated because you've got lots of things to find out and lots of different things to find out. So a really good skill in physics to learn is when you've got a complicated problem, break it down into smaller, simpler problems and then build it up. So let's start by looking at the current because that's what we did earlier on. We're still using the same rules. So first of all, is I1 in series or parallel? Well, it's in series because there's only one way for the current to flow. But then when it gets to I2, we see that it splits up. So the next question is, are the bulbs identical? We assume they are. So the current must split up equally. So that means I2 must be 1.5 amps here. And if we were asked about the current over here, it would be 1.5 amps again. The current then joins up again to go back to the cell. So that gives us a total of 3 amps as our supply current. Okay, so hopefully you got that. The voltages we can now focus on. And again, we think about is it series or parallel? It's in series. So that means the voltage must split up across V3 and the parallel bits. This should really be V5 there, I've just noticed. So if we know V5 is 2 volts, what's V4? Well, voltages in parallel are constant, so that means this must be 2 volts as well. And so therefore, if there's 2 volts here, there's 2 volts here, that gives us a total of 4. Subtract that from 6, which means we've got another 2 volts across V1. Okay, and hopefully you got the same answer as well. If you didn't, review what we've talked about, remember that process, identify if it's series or parallel, use the rules for series circuits or the rules for parallel circuits to work out either the voltage or the current. Got a few questions for you to try with the tutorials. As always, just upload it onto Teams and I'll give you feedback, folks. Thanks for listening and hope to speak to you again soon.